welcome to the seminars. I just wanted to remind you that eating and drinking is prohibited in this room. The speaker of today is Dr. Alon Rimmer from the Kinetic Limnological Laboratory. Dr. Rimmer completed his doctoral studies at the Technion at the Agriculture Engineering faculty. He was teaching several courses at the Technion, at the Tech College, Kinetic Engineering College, and University of Freiburg in Germany. The areas of the expertise are hydrological and limnological modeling, lakes water solute energy balance, lake salinization processes, and models of lake stratification and its effect on lake chemistry and biology. Please.
Okay, I want to thank Regina for inviting me, and I will do my best to present the subject. I'm going to talk about, as you see, mechanisms of long-term variations of the thermal structure in a warm lake. Now, when you look at the long-term, usually everyone now is connecting everything to climate change. And if you see a long-term change, then you immediately tie it to some kind of climate change, and by that you find the solution. And I want to show you this study just to demonstrate that not all the long-term changes are climate change. There are other changes which should be taken into account before you go to this buzzword. Okay, seasonal and interseasonal changes in lake stratification, and in the quantities I will talk about later about what is stratification, and in the quantities and the concentration of chemical elements in two layers are important in determining the behavior of biological system of the lake and determining water quality. Observations and finding related to the thermal structure of the stratification and transformation over the years, and the connection of stratification to water levels and water balances are essential for understanding the ecological system and its stability. I want to put it in a large context of why do we look at seasonal and interseasonal stratification. Basically, when you look at the lake situation or at the lake chemistry or physiology or ecology, you always build it on top of the physical state of the lake. So the stratification is very important in order to take the next step of looking at the ecology and geochemistry. So the goals are to examine and quantify the changes in the lake thermal stratification over 40 years, between 1969 and 2009, how the thickness of the Epilimnion, Metalimnion, and Hypolimnion changed over time, and what factors influence the change, whether there have been changes over time in Epilimnion and Hypolimnion temperature. Is it possible to explain the results using operational, climatic, biological, and or hydrological data? There is a lot of research now about lake temperature, again, because of climate change. Many groups, and I'm involved in part of them, are looking for the lake temperature worldwide. And you will see here that you should be somehow cautious about your conclusions on each lake that you examine. Let's see what the temperature profile measurements are. Very simple. The study is based on 40 years of weekly measurements of the temperature profile of the lake water. During this study, about 1,800 temperature profiles were examined. This is the lake. This is the temperature. Sometimes the lake is stratified, sometimes it's not, which means sometimes it's hot here and cold here, and during the winter it's fully mixed. I will not get into these aspects because it's, to the physical aspect of this, because it's totally different lecture. But I will explain what the profile looks like. Okay, so we have measurements every week for 40 years. Now it's more, it's 45 years. And each week we have the measurements from 0 to 40 meters in the middle of the lake. Also, we have measurements here and here, but these were not taken into account into this study. The only thing that I tested was 1,800 measurements throughout the years. Now, when you look at the stratification during the years, you see these two pictures. This is 40 years ago, about 40 years ago, 1970 to 1975, which means I took the average stratification of these years, which means this is the date or the month, and this is the depth. And this is the temperature at each time and at each depth. And this is very typical to Lake Kinneret. If you look at papers about the physical structure of Lake Kinneret, you will see a picture like this. You always find it. So this is August, this is warm, this is January, it's fully mixed. The entire profile is fully mixed. And this is January next year, which is fully mixed again, okay? And during this time, the lake is stratified, hot on the top and cold at the bottom. But if you take a look and compare between this and this, you will see that during 2004 and 2009, the profile looks a little bit different than the profile here. And since it's an average of 5 years, it cannot be some kind of arbitrary difference. It's kind of solid difference. Okay? So if you put one of them on the other, which means you subtract one profile of temperature from the other, this is the profile that you get. And what you clearly see is that the depth of the stratification reduced throughout the years, which means the stratification now is less deep. Okay, the temperature doesn't reach as deep as here. It's less deep. And the other thing, that higher Epilimnion temperature by about 1.5 degrees. Now you look at this and you say, okay, climate change. Okay, right? Because during the 40 years there was a change of 1.5 years. Immediately you say, obviously this is climate change, isn't it? Okay. Let's see, what is the possible causes of stratification changes? We look at climatic data, which means it can be changes in solar radiation. I don't know if you heard about global dimming, but it's a kind of global phenomena that was observed mainly during 20 years ago, that they say that the sun, that the radiation is reducing. Now it's not very popular, but you can find it in the literature. It's there. External temperature changes, global warming. This is another thing that can cause stratification changes. And there is a possibility that winds were changing. Winds, if the wind is stronger, then the mixing of the lake is stronger, and then you will find different stratification. There are other data that can change, operational and hydrological variables. Let's say that we look at lake level changes. Maybe the level of the lake changed, and this is what causes the difference in stratification. Changes in water input and production regime, which means maybe the input and the output of water into the lake or out from the lake also changed during the years, and this is what caused the changes of stratification. Biological data, changes in turbidity. If the lake is more turbid, then the radiation is less into the deep parts of the lake, and stratification changes. Each one of these can change the stratification. By the way, I started this research, and I was sure that this is the cause, changes in water input and production regime. I was sure because I knew that there was a change in water inputs and production, and I was absolutely sure that this is the cause for the stratification changes. And then I started to check it, and I found that I was totally wrong. Let's look at long-term changes. Okay, we just showed you what might be the causes for changes. All these. Let's look at the real changes that occurred. Long-term changes, lake level. Lake level during these years looks like that. It goes up and down, up and down. It goes down here, goes up again here, goes down here. On the average, the lake level is reducing. Now we probably are in different time. So lake level will rise a little because of desalinization, but this was what we knew at 2010 when we did this research. Long-term changes, let's look at air temperature. Air temperature is obviously rising in Mount Canaan, on the eastern Galilee, in Kfar Blum, in Hula Valley, and in Lake Kinneret. Above Lake Kinneret, we didn't see long-term changes. But these are the changes in the environment in the region of the Lake Kinneret, and we can see that it obviously changed during the years by 1 degree. By the way, this was not a study about how the air temperature was changed, but we took references and we saw that these data are well documented by climate scientists. So these are long-term changes, air temperature. What can be another reason? Available water, which means the water that goes into the lake. You can see that during these years, or during many years, the water into the lake is decreasing. The amount of water that goes into Lake Kinneret is decreasing. I will not elaborate about it too much, but it's partly because of changes in rainfall and partly because there is increase in water usage in the watershed, and therefore less water are entering Lake Kinneret. So this is long-term changes number 3. Long-term changes number 4, water turbidity. This was found in Canada in several places. It was found that this changed the stratification of several lakes. In our lake, you can't see anything. It's all very, very stable. The turbidity of Lake Kinneret and the KD is the constant of reduction of the exponential decay. Never mind, it depends, it's part of the turbidity measurements, and you can see that it stayed constant throughout 40 years. And long-term changes, 5 short-wave radiation. Okay, also you can see this is the central line which take averages of all these points. Each point is each color is different month, and you can see that radiation didn't change. We cannot see any change in radiation throughout the year. Okay, so I told you that at the beginning I thought that this was the main cause, the inflows and outflows. I thought that this was the main cause for the stratification change. But then we looked at the monthly heat budget of the Lake Kinneret, which was also some kind of, this was a project that is done continuously, so we have a very good calculation of monthly heat budget of the lake. And what you can see from this heat budget is that this is the net radiation, which is the largest part of the heat budget of the lake. And then you have the latent heat. The latent heat is, actually it should be from here down because it's leaving the lake, okay? But you see it's also a big quantity. These two are the big quantities of energy, inflows and outflows. All the other parts are much smaller. Heat storage, sensible heat, vapor heat, H in, which is the amount of heat from the inflows, and H out, amount of heat from the outflows. Which means that, and the red heat storage change is actually the residual. Okay, it's the part that remain in the lake after the inflows and outflows. So when you look at the graph and you look for some quantity of heat that will change the stratification, it's better to look at the big numbers, not at the small numbers. Because how much this small amount of water can change the heat of the lake? It's very small. It can hardly change anything. So if you look at what is the causes for the changes of the heat of the lake, it's better to look at the big numbers, which means the net radiation and the latent heat. So when I saw this and when I realized these numbers, I had a feeling that I have to go into other direction, which means not to take into account the inflows and outflows, but look at something which is connected to the radiation or the latent heat. Now, if you remember, the radiation didn't change at all. So, conclusion, expected changes of thermal stratification are mainly due to changes that affect the radiation and latent heat flux. This is the main conclusion from this graph. Okay, so now let's look at the analysis of the data, what we did with the data. Each profile of heat in the lake is measured, is given here by the points, and I wanted to develop a model that will not let me judge by my own feelings how the stratification, what is the stratification here. So the idea was to build a kind of simple model that describe these points. And this equation actually describe some kind of approximation to this point. Now, when you take this and you make an optimization process, you can reach this kind of graph, and from this kind of graph, you can come out with this exact number, and by putting the by putting this line, you can find this point, and you can find this point, and then by doing that, we have a kind of estimation for the hypolimnion, okay, from here to here, the metalimnion from here to here, and the epilimnion from here to here. Which means every measurement, every one measurement of the 1,800 measurements can be approximated by a line like this, and then we can pull out the number which is typical for the hypolimnion, that metalimnion, and the epilimnion. And we can look also at the temperature here, at the temperature here, and at the stratification, at the gradient of heat. So this is what we did, and this is typical for several, just 4 typical profiles. This is April 97, this is July 97, this is September 97, and this is December. You see that it changes throughout the year, and each profile I can come up with an equation that describes this, and come up with parameters that describe exactly the epilimnion, the metalimnion, and the hypolimnion. So when we look at this, and we operate it on 3 seasons, so that's what we get. Don't simply ignore this, because these are not real numbers. This is the time when the lake is mixed. So these are numbers which you shouldn't take into account. It just the computer brings it out. But what you look at is this. This is where the thermocline is throughout the stratification period. And this is the upper part, which means from here to here is the epilimnion, from here to here it's the metalimnion, and from this line to the bottom it's the hypolimnion. So we have 40 years of lines like this, and then we can take these values and divide it into April, May, June, July, August, and look how it changed throughout the years. Is it clear, this idea? Okay, we look at, for each year, we look each week, and then for each week, for each month, we make kind of average, and then we look at the multi-average of all the years, and that's what we get. Okay, stratification changes. Depth of the epilimnion for December, November, etc. Okay, each color is a different month, and this is the years. What we can see is the epilimnion depth throughout the time is kind of reducing a little, but it's not very obvious. Okay? Now let's look at this. This is much more. The thickness of the Epilimnion. Epilimnion is the middle layer. The Epilimnion reduce in time. You can see it clearly for every month. You can see that the Epilimnion becomes smaller with time. And temperature of the Epilimnion, temperature of the upper layer, increased during the time. Okay? You can see it also very clearly here. Hypolimnion, which means the bottom layer, didn't change. Almost didn't change. It stays nearly constant. It almost didn't change. Now I'm doing some other work on the hypolimnion temperature, but it's not connected to this one. But it stayed the same. And thermocline depth reduced with time. Thermocline is actually, if you remember, this middle line. Okay, this is the thermocline. So if you look at it for each month along the years, you will see that it is reducing in time. So basically, let's look at the summary of these findings. The level of 9070 was on average higher than, which means the lake level was on average higher than the lake level in 2000 and after. The Epilimnion of 9070 and the Epilimnion of 2000 were somehow the same, although they are a little bit different. The Epilimnion temperature of 9070 is smaller than the Epilimnion temperature in 2000. Metalimnion is larger in 9070. Hypolimnion is almost equal, and hypolimnion with star, which is, if you take it from the thermocline to the bottom, is larger. Which means I have read different characteristics for the year 2000 or for the years of 2000 and for 9070. So now I have results of the stratification. And I showed you what can cause these changes. And this is another, okay. So what I thought is maybe I should try and look for the impact of lake level. Because you remember I said that the inflows and outflows has very little amount of heat. So they can contribute very little to the change of heat. Radiation remained constant. But maybe something else, which is not the radiation, caused the radiation to act differently on the lake. And what can be this, what can cause it? If the lake level reduce. If the lake level reduce, it means that the surface of the lake and the amount of heat stored in the Epilimnion, again, if the lake reduces, the lake surface changes, but the volume changes in a different way. Okay, let's say that the surface is changing by 2%, the volume may change by 10%. The volume of the upper part, because of the different bathymetry of the lake. And here I did some kind of analysis. I'll show you it in a minute, and you can see in Lake Kinneret that if you keep the Epilimnion if you keep the Epilimnion in the same amount of meters when the lake level is high and when the lake level is low, there is a change of surface to volume. And if there is a change of surface to volume, there must be an additional heat or less heat in the upper layer, and then something must change. You understand the argument? It cannot stay the same because the volume here changes not according to the lake surface. It's a little bit difficult argument, but that's what you see. Surface area over Epilimnion volume. This is 1. This is typically what happens, a typical level. And then what happens if you reduce the lake level from minus 215 or increase the lake level from 215 to minus 209. You see that this ratio changes. And the change of the ratio means that actually the effect of the radiation changes. And that's exactly what I thought will happen. The radiation did not change, but the effect of radiation changed because the lake level reduced. So, if you take the same numbers that I showed you before, I mean the same values that I showed you here, and you put them not against the years, but you put them against lake level, okay? Then you see something very clear. You see that the hypolimnion thickness reducing. You see that the metalimnion thickness reducing. The epilimnion is almost doesn't change. The temperature is rising, and this is all against the lake level. It has nothing to do with the time. It has to do with the lake level. And even the hypolimnion temperature is rising. And this is the stratification. The stratification is changing. Okay, and this is all due to changes of lake level. It has nothing to do with the time. It has nothing to do with climate change, which is a phenomena of time. And if you look at the stratification period, which means when the stratification started and when the stratification ended, you also see that the lake level has an effect, which means the stratification is taking longer time, which means almost 300 days or more than 300 days when the lake level is low, and 260 days when the lake level is high. So obviously you can see that the lake level is the and very important factor in the stratification and in the lake thermal condition. Now, who is on charge of the lake level or lake kinetic level? Who is on charge? You probably know. It's not God. Huh? It's the water authority. Okay? So, most of it is because of the water authority, the amount of water they take. So if the effect of lake level is such, it means that what you see here is not climate change, it's operational policy change. Okay? You must understand it because that's a very important point. Not everything that you see in the lake or in the whatever is because of climate change. It might be something totally different. in order to be sure that we are not just playing with numbers, with measured numbers, we used the DYRESM, which is a model built by an Australian group in water resources, how do they call it? CWR, Center of Water Research in Perth, in Australia. It's very, very famous model. And we tried to do exactly, we tried some kind of experiment. We ran the model on two levels of minus 216 and minus 210. Okay? Very different levels, which means it changed also the model is taking also into account the bathymetry of the lake. So it took the lake as if it was in minus 210 and minus 216. And then we also added a scenario in which we put different air temperature as forcing on the lake. Okay, so the variables were different levels and different air temperature. And we just wanted to see if according to DYRESM, we will get results which are in agreement with what we found. So stratification change due to changes in lake level were examined. The model showed changes similar to those observed in practice. The results have been tested and found statistically significant. And here you can see graphs of Epilimnion thickness and Metalimnion thickness and Hypolimnion thickness, and each color with points is from the model, and each line is from the reality. Now we didn't care about the fact that this line is here and this line is here. We just concerned the trend. Here it's reducing and here it's reducing, almost by the same level. And this is reducing and this is reducing. Okay? That's what we wanted to see. We didn't care about the exact location because we cannot show with the model exactly the stratification of the lake. We can just show that during the time it changes. Okay, so we showed in the model, I will not get into this. I will just say, just show you this, that changes due to lake level change of the Epilimnion thickness were larger, or even I would say were larger when we showed it in the model. It was larger due to lake level than due to air temperature. And that was exactly what we found not using the model. We just from the data itself. So the model showed us that the ideas that we have are actually verified by the model. Now, there are two other things that need to be taken care of. Let's look at the Epilimnion depth according to net water inputs. Okay, I told you before that there might be an effect of water input on the stratification. And what we found was that only during April and December there was a reduction in the Epilimnion thickness because of the inflows and outflows. Now, why is it like that? Because when the lake is stratified, and you put in a lot of water from the outside, the water from the outside are staying at the top of the lake. They don't go down. So they make the Epilimnion larger. And when it is happening that the lake is stratified and there are large flows, only in December, in the beginning of the rainy season, and in April, in the end of April, at the end of the rainy season, when the lake is both stratified and there are large inflows. All the other months, you cannot see anything. July, October, the inflows and outflows doesn't have any effect. So this was something else that we checked. But again, compared to the effect of the lake level, this was very minor effect. It was almost negligible. So, in summary, the main reasons for changes of thermal stratification. Changes in solar radiation. No evidence of significant changes in solar radiation. External temperature change. Air temperature increase was observed in the Jordan Basin. Work with the model didn't result in significant conclusion about the effect of temperature on stratification. Lake level changes, data, simple physical considerations, and working with the model indicate that the stratification change can be attributed to the change in lake level. Change in water input and production regime. The effect is typical, apparently only for April and December, because of the combination between stratification and amount of inflows. Changes in the turbidity, we found no significant evidence that this factor has an impact. Changes in the prevailing winds, not thoroughly tested due to the difficulty of finding a series of wind measurements. Actually, this could be a serious candidate, but there are no data available, and we don't know if it changed. We don't think that the winds over Lake Kinneret changed that much. So the final conclusion is basically this, that what we see is mostly because of lake level changes and not because of other causes, or let's say that this is the dominant cause and all the others are much smaller. That's it. That's my...
Okay, thank you very much, Alon. Any questions, please?
Yes.
Can you go back again? You did show that the lake became hotter, like so between 1970 and 2010. Can you show us again why it doesn't affect? You said at the end it doesn't affect the depths of the layers.
What do you mean?
You show the connection between the heat of the upper layer,
Yeah.
and if it affects the depths of the layers. But then you said the climate change doesn't affect it.
Because what is climate change? Climate change, when you look at also at other publications, you look at air temperature. There is no other. I mean, most of the analysis, they said, okay, let's look at the air temperature, because this is the main cause. They said the world is warming, so let's look at climate change. Other causes can be like changing of winds and things like this, but we couldn't check it. But the temperature of the air, you could obviously see that the temperature of the air in our region was changing, and it was tested and verified by experts much bigger than myself. But when you look at the lake physics, you see that the air temperature is the cause of, I'll show you. is the cause of the sensible heat flux. Okay? Sensible heat flux is the difference between the heat of the air and the heat of the water. Sensible heat flux is this. Okay? You see? Very small. And if you see a large change in the stratification, and we can see it obviously because the difference in the stratification is very obvious. To look for this factor as the ruling factor, and it's not that we just say it, we tested it, and we couldn't see any evidence that this is affecting more than, I don't know, it affects but has very little effect compared to this net radiation that didn't change, but the ratio of this, how it goes into the surface and how it hits the upper layer is changing. Okay, I hope I have a better explanation now with mathematics and so, but let's leave it for next lecture. Yes.
What is the long-term consequence of dropping of water level in the lake itself?
We now try to preach more to the keeping the lake steady. The reduction of the lake, I mean, we think this is somehow the natural fluctuations of the lake. When you look at these are man-made fluctuations, okay? Because the annual normal or natural fluctuations are this. So we know that it's used for water as water reservoir of the state of Israel, but we try to say, okay, try to keep it between, let's say, this level, around this level, that it will go up and down 1.5 meters and not more than that. The problem with these amounts is, for example, when the lake level drops to this number, there start to be weeds on the edges and it grows up, and then when it comes up, it's all full with weeds and mosquitoes. There are changes in the fish population. Several decades before, people thought that low lake level will cause increase in solute water inflows, which was found not true, actually. We now know that it's not true. There will not be any extra salinization due to low lake level. But there are still many environmental aspects that we simply think that the lake should be in some kind of constant level with fluctuations which are small fluctuations, like 1.5 meters, not more than that. So, is that okay?
Okay, any other questions? Yeah, please.
The last 3 years, we stopped taking water from the Kinneret. We compared the results of this research with the last few years.
I couldn't understand.
In the last 3 years, due
Yeah.
to the desalination of seawater,
Yeah,
the pumping of the Kinneret has reduced. So,
yeah, exactly.
so the water level should have risen.
Yeah.
And have you compared the results of this research with recent years?
No.
And,
No, not yet, but it will be interesting, actually, after several years, because you see that there are many fluctuations. But after, let's say, 10 years, if the lake level will be like that again, during these years, it will return here, then it will be interesting to see if the results are still the same. I don't know. So far, oh, never mind. I had other research in other fields that I said this is what's going to happen, and so far it was right. So I hope in this case I will also be right. Otherwise, you know, I did my best.
Okay, any other questions? Yes, please.
First of all, it makes sense, the water level and the changes you see, but I wonder if you compare years with same level to try and isolate that factor.
What do you mean?
If you took, let's say, I don't know, 78, 79, and 87, which are
to
seem
look
to be
at
the same.
2 years with
I don't say, don't have to be 2 years, but years with the same water level, to try and take that out.
the entire analysis is taking water level as the independent variable here. So I don't have to separate 2 years. I took all the years, and you can see that the lines have a very obvious
So
trend.
this is the whole period.
Huh?
This is the 40 years. This is not only
Yeah.
the difference you see.
This is the 40 years of data. So you can see here actually, I think you have 40 points here.
Okay.
Okay, thank you very much, Alon.
You're welcome.